Hi everyone, today's video is going to be focusing on answering question 31 of the Maths CSSA Maths Advanced trial paper. So this is the last question in the paper. Thought it was a good one to go through. It's 5 marks and there's a lot of parts to it, so it can seem a little bit challenging at first. I think it's a good one to go through in terms of how to approach difficult questions like this. Generally, the idea is that we want to start by highlighting any key information and working from the start of the question and then downwards. So hopefully this helps to kind of tackle harder questions, especially comprehension ones. So let's have a look at this question. We have two graphs, y is equal to x squared and y is equal to ln x plus k, and they intersect at the point A. We're told that these two curves share a common tangent at point A, and the primitive of ln x is given to us here. We're told that by finding the coordinates of point A and the value of k, show that the area bounded by the curves and the x-axis is this value here, correct to 4 significant figures. Okay, so straight away there's a lot of information given to us. You might have noticed that I'm actually already going to be highlighting while I'm reading out the question. I think that's a great thing to do to see what kind of points pops up straight away for you in an exam. Or you can always go back and highlight things afterwards. So if I'm looking at this question kind of chronologically, the first thing I'm having a look at is the fact that these two curves share a common tangent. So when two curves share a common tangent, that means that at this particular point here, they're going to have a common tangent and equal tangent, which means that the gradients of the tangents at that particular x point are going to be the same. So if I'm looking at the gradient of the tangent, I know that I'm already going to be working with my first derivative. So that's probably my first hint on how I can get started with this question. So I'm going to be having a look at finding the derivative of first y is equal to x squared, which is just going to be 2x. I'm then going to be having a look at finding the derivative of ln x plus k, which, because k is a constant, is just going to be 1 on x. So just the derivative of y is equal to ln x. Now, because I know that these gradients are going to be equal to one another, I can equate their tangents. So I'm going to say 2x is going to equal to 1 on x. Timesing both sides by x, I get 2x squared is equal to 1. Dividing by 2, I get x squared is equal to a half. And then the last thing that I need to do to make x a subject is take the square root of a half. So when I take the square root, it's super important that I take the plus minus a half as well. However, with this particular question, I can see that my a value is going to have a positive x value since it's on the positive side of my x-axis. So I'm going to just take the positive root version here. However, I do need to acknowledge to the marker that I've noticed that I'm taking the positive, the square root. So I'm going to actually neglect the negative value because x has to be greater than 0. That's really important to make sure that we don't lose any marks in questions like this. But perfect. So now that we know the a coordinate, the x coordinate of the a value is 1 on root 2. So this value here is 1 on root 2. To find the corresponding y value, I then need to plug it into either one of my equations. So using the fact that y is equal to x squared intersects at point A, I'm going to say y is now going to equal to 1 on root 2 squared, which is equal to a half. So therefore, my coordinates at point A is going to be 1 on root 2 and positive a half. Perfect. Okay, so now I've done this first part of the question. I found the coordinates of point A. I can then continue reading my question chronologically, and it says that I need to find the value of k. So when they say k, they're referring to this value here, which is how much my graph of y is equal to ln x has shifted upwards or downwards by. So if I'm trying to find the value of k, I'm going to use the fact that they are intersecting at this point at point A. So when two graphs intersect each other, that means that they're equaling one another. So I'm going to take and equate my y values of both of my functions, so y is equal to x squared and y is equal to ln x plus k, and let them equal to each other. So I'm going to get x squared is equal to ln x plus k. I know that at my particular x value that they intersect is when x is equal to 1 on root 2. So I'm going to substitute in 1 on root 2 into my x values. Then all I need to do is rearrange so that I'm making k the subject here. And I get that k is going to equal to 1 on root 2 squared, which is a half, minus ln of 1 on root 2. And now I've just done the next part of my question, which is finding the value of k. I can now move on to showing that the area bounded by the curves is that value there. To find the area bounded by these curves, I'm going to use the approach that the area is going to be this area here minus this area here. So to make this a bit easier, I'm going to label this A1 and A2. And I'm going to say that the area bounded by the two curves is going to be area 1 minus my area 2. So the values that I need here is I've got this 0 function here. I've got the x value of my y, of my a coordinate, going to be 1 on root 2. And I also need to find where my y is equal to ln x plus k graph intercepts the x-axis. So when I have an x-intercept, that means that I have when y is equal to 0. So I'm going to let y is equal to 0 into ln x plus k. So therefore, substituting in my value of k that I found, I get 0 is equal to ln x plus a half minus ln 1 on root 2. And then I want to keep solving for x. So I'm going to get x is equal to, so ln x is equal to negative a half plus ln 1 on root 2. And therefore I'm going to then find my x by raising both sides to the power of e. So x is going to equal to e to the negative a half plus ln 1 on root 2. And that's my value at this coordinate here. So I can then start to find my expressions for my a1 and my a2. So a1 is just going to be the integral of between 1 on root 2 to 0 and x squared dx. So this one's going to be x cubed on 3 within my domain of root 2 and 0. And once you evaluate that, this integral here is equal to 0.117851, just minus 0, which is just equal to that value there. A2 is a little bit more complicated, so I'm looking at this value in here now, so this area prescribed in here. So my domain is instead going to be between, still my top upper bound is going to be 1 on root 2, but my lower bound is just going to be that x-intercept that I just found. So it's going to be e to the power of ln 1 on root 2 minus a half. And then I'm integrating my ln x plus k dx. Now, usually within the Maths Advanced course, we don't need to actually integrate ln x, which is why they've given us this condition here. So they've told us already what the integral of ln x is going to be, and we just have to substitute that in. So I'm going to expand out the brackets to what they've given me here, and I'm going to get x ln x plus x. And this k value here is just a constant, so this is just going to be kx like that. We can substitute the value of k in later, just so that it doesn't get too messy at the moment. So we get 1 on root 2 and still my e to the ln 1 on root 2 minus 1 half. Then I want to do the big task of substituting everything in. So what I'm going to get is I'm going to get x ln x plus a half minus ln 1 on root 2 x between my same domains. Okay, all you would do here is substitute it first with your x is equal to 1 on root 2, and then when your with your e to the ln 1 on root 2 minus a half. And what you get there then is that you get this value here is equal to 0.0753267, and so on. So finally, to find the total area, like we said before, it's going to be area of the first one minus the area of the second one. So we get 0.117851 minus 0.0753267, which is giving us 0.0425 1.52 units squared, which is exactly what we wanted to prove at the start of this question. So quite a lengthy and tedious question, especially when it comes to substituting in at the end. But hopefully this helped in terms of how we can comprehend questions that are this kind of length and how we can work from the top of the question and then all the way down as well.